need to be going on. And they all happen simultaneously. I've listed them in the order that they would occur to oxygen coming into the body. But I could just as easily have listed them in reverse order based on the order in which carbon dioxide would move out of the body. So we're constantly bringing oxygen in, we're constantly sending CO2 out by this combination of four processes. Of course, the reason we need to do that at all, the reason the body requires oxygen, the reason it has all this carbon dioxide to get rid of, is due to cellular respiration. Cellular respiration is not part of this, it's the reason for this. And it happens in individual cells, each one doing it all by itself. So it's not an organ system process. Cellular respiration is a cell-level process happening everywhere in the body. Now, respiration on the organ system scale, the primary job carried out by our respiratory system, that's going to involve four different tasks that need to happen correctly for it to occur. We need to move air in and out of our respiratory system, do what we call ventilation. Ventilation is simply a matter of moving air from point A to point B and back to point A again. It's breathing. And this takes place in what we call the conducting zone of the respiratory system, passages that give air access to the interior of the lungs, where the next stage, external respiration, can take place. So when you hear the word breathing, think ventilation. It's not actually changing the chemistry of the gases at this point, not adding anything to the air or subtracting anything from it. It's just moving it from place to place. We'll see how ventilation occurs and how we use differences in pressure to move air from one place to another on Wednesday. Now, the goal of getting air into the lungs is to bring in oxygen that can be absorbed into the bloodstream. Likewise, expelling air, the goal with that is to get rid of the air the oxygen's been taken out of, and also get rid of carbon dioxide that's been added to that air. Moving oxygen and CO2 in and out of the bloodstream, respectively, that's called external respiration. It doesn't happen outside the body, it happens in the lungs. But because it involves air that came from outside the body, it involves your body interacting with the outside world. Your tissues, in this case your lungs tissues and the blood flowing through the lungs, interacting with something from outside. So external respiration, it's not that it happens outside the body's surface, if that involves something drawn in from outside, external air. And in this process, oxygen is going to be absorbed from inhaled air into the bloodstream by diffusion. CO2 is going to leave the bloodstream and enter the air, which can then be exhaled from your alveoli out into the environment. That's as far as the respiratory system itself is going to take this series of steps. So it's the first two stages that are actually being carried out by the respiratory system proper. Gas transport, that's where the bloodstream is going to take over the job. So, in gas transport, oxygen is put into the blood, but it needs to be kept there long enough for it to be transferred from the lungs out to the surrounding tissues of the body, out from the pulmonary circuit where it enters to the systemic circuit where it's needed. Likewise, carbon dioxide picked up in the systemic capillaries from surrounding tissues needs to be moved to the lungs. This is surprisingly tricky to do because it turns out that neither of these gases, oxygen or carbon dioxide, is terribly water soluble. CO2 is a little more soluble than oxygen, but neither of them blend with water terribly well. So our bloodstream needs to use tricks like hemoglobin to carry these gases for a sufficient amount of time to move it between the pulmonary circuit and the systemic circuit. We'll see some of the different ways that these respiratory gases are handled while they're in the bloodstream so that they don't turn into bubbles while they're still in the blood, still in their journey. Make sense? At the end of the oxygen's journey and the start of the carbon dioxide's journey, we have internal respiration. This is an exchange of gases between the bloodstream and systemic tissues. So our systemic capillaries, that's where this is going to happen. Everywhere in the body that's not alveoli and alveolar ducts of the lungs, we're going to have CO2 entering the bloodstream, CO2 produced by cellular respiration that we have to get rid of, and oxygen leaving the bloodstream to go to the tissue that needs it. We're going to see some of the ways that the body fine-tunes how much oxygen is dropped off to make sure that each area of tissue gets the right amount, depending on whether that tissue is working hard and consuming lots of oxygen, or taking it more easy and not needing as much. So internal respiration, there's no involvement of external air there. We're way past the air at this point. So that's what we call this the internal respiration as opposed to external, which is between air and blood. All of these processes involve handling the same two gases, oxygen and CO2, or handling air that contains a mix of those two gases in the case of ventilation. So that's why we all consider them parts of the respiratory process. Make sense? Now, of these processes, as I said, it's just the first two, ventilation and external respiration, in which the respiratory system organs actually are actively involved. They do have some passive involvement in internal respiration in that most of them do require the bloodstream to deliver them oxygen for their own use and carry away the CO2 they produce. But their contribution to this process is all in the first two steps. So we'll see what the respiratory organs do for these processes, and then we'll see the bloodstream taking over the duties as we move beyond the first two steps in the next few lectures. Now, of the structures that are carrying out those first two steps, we can divide them up into the conducting zone, the passages that allow for ventilation, the movement of air in and out, and the respiratory zone, structures which receive the incoming air and have thin enough walls for oxygen to be dissolved into the bloodstream, CO2 to pass out of the bloodstream. So conducting zone, getting air to and from the respiratory zone. The lungs are where the respiratory zone is, and even not all of the lungs are part of it, just the areas where the walls are extremely thin, allowing for gas exchange. Why are your lungs taking up such a big part of your chest? Because the respiratory zone needs to have three qualities to be effective as a place where you can exchange gases, where you can perform your external respiration between air and the blood. It has to be big. It has to have a lot of surface area, providing surfaces through which oxygen and CO2 can pass by diffusion. It has to be thin. Again, we consider it to have become the respiratory zone when the walls of the spaces the air is traveling through get thin enough for gases to move through them in and out of the bloodstream. And it has to be moist. It turns out that moisture on the surfaces that the air is going to move in oxygen into, having those surfaces be moist makes it much easier for the oxygen to pass into the bloodstream. The bloodstream is full of water with lots of plasma proteins and so on in it. That means in order to get into the blood, oxygen has to dissolve into water. And having a little moisture on the surface that's going to pass through to get to the blood makes that dissolving of oxygen much easier. So thin, moist, and large. The lungs take up a substantial part of your thoracic cavity because that's how you fit in enough surface area. That and constructing them out of microscopic bubbles, each tiny bubble, each tiny bag, each little alveolus, and more surface area for gas exchange. If you were to take all the alveoli in your lungs and all the other respiratory zone surfaces, like the linings of your smallest bronchi, spread them out, they'd cover a tennis court. Much bigger area than, say, your skin would have. So a lot of surface area packed into two fairly large thoracic organs. Make sense? Now, to get air to those thoracic organs, we need to make sure that it's in good condition. Of the respiratory tract, the upper portion in particular, the nasal cavity especially, is equipped to trap incoming particles. Much of the lower tract is as well. When we breathe air, usually we're not breathing completely clean air. There's particles of dust, of smoke, of odors suspended in the air. Our upper respiratory tract, structures of the conducting zone before the larynx, nearly all of its surface is covered in pseudostratified epithelium with cilia and mucus on its surface. That's what we find inside our nasal passages and inside the upper part of the pharynx, because food moves then through those areas and could potentially scrape off cilia and mucus on their way to the esophagus. But this upper part of the tract, and especially the plates of bone called nasal conchae that hang down inside each side of the nasal cavity, they are covered with mucus and cilia. Now, you might remember seeing the nasal conchae in A&P1 when you looked inside the nasal cavities of the skull, these bony curtains hanging down on either side of the middle septum of the nasal passages. Their coating of mucus helps to moisten incoming air. The large number of blood vessels just under the surface of their mucous membrane helps to warm incoming air. So if you're breathing cold air or dry air, that's going to help to humidify and heat up the air, make it more tolerable for your lungs when it's drawn deeper into the system. The mucus itself is also a trap. It's sticky like flypaper. When you inhale foreign particles into your nasal passages along with air, those particles, pollen, smoke, soot, pollution, and especially things like viruses and bacteria, your body's trying to use its mucus on the walls of those conchae to trap those incoming particles in the mucus, prevent them from passing further down into the lungs themselves. So you're using the mucus like flypaper to trap incoming materials. If you're exposed to a lot of incoming materials, you may also activate sneezing as a reflex to clear out those materials, sending a blast of air that will expel them from the nasal passages. If your nasal lining is irritated, you'll produce more mucus to increase the odds of trapping particles. That's why you get a runny or stuffy nose if you have serious irritation to the nasal passages, like if you have an allergy to pollen and are breathing lots of pollen. So, trapping incoming particles, warming the air, moistening the air, all these things are going to try to condition the air, make it safer for your lower respiratory tract and eventually your lungs. Make sense? Your oral cavity provides a backup route. If you make so much mucus in your nasal passages that air can't get through in sufficient amounts, you can breathe in through your oral cavity. You also exhale through your oral cavity when you speak. Now, the lower respiratory tract is considered to start at the larynx. That's because that's where you have the option of sealing off your lower tract from the rest. It's at your larynx. The epiglottis at the superior end of the larynx, you probably heard a bit about that in A&P1, I'm sure you heard about it in lab. That structure can fold down to cover the glottis, the orifice into the top of the larynx, thus blocking off incoming air from going down the trachea, thus trapping air in the lower tract that's already there. We use the epiglottis for several purposes. We can use it to prevent choking or inhaling of liquids when we're eating. Aspiration is what we call it when we inhale material that's not air into the respiratory tract. We want to avoid that because at a minimum, it'll leave us coughing, trying to expel whatever went down the wrong pipe. In more severe cases, if we accidentally inhale something large enough and solid enough, it can get lodged in the lower tract and obstruct breathing. That's what causes choking. Something is obstructing the flow of air through the larynx or trachea below. So the epiglottis, primarily a defense against choking. And it closes by reflex when we swallow. We'll see swallowing in our next unit when we look at the digestive system and the role of the epiglottis in protecting us from aspiration. The larynx also can close the epiglottis when we need to hold our breath. If you jump in a lake, if you go swimming, the epiglottis folding down is what really stops you from inhaling water. Now, it's not just that you stop taking action to breathe, it's not just that you close your mouth. Yes, you can close your mouth when you jump in water to avoid getting water in your mouth, but you can't seal your nasal passages. You don't have a mechanism to seal that orifice. What really stops you from inhaling water, if you fall into water, if you go swimming, is folding the epiglottis down and keeping it down while you are submerged. The epiglottis also allows us to perform what's called the Valsalva maneuver. When we lower the epiglottis, whatever air is in the